Hi, my name is Mark Bailey. I'm an application engineer here at Agilent Technologies, and today we're actually in the standards lab here in Loveland, Colorado. With me today is Stan Pond. Stan is the owner of Ponds Engineering. One of his specialties is making accurate measurements and actually creating instruments that will render triple points, triple point of water, triple point of other materials.
Yes, precision thermometry.
Precision thermometry, okay. And one of the first questions you might have, I did, was, wait a minute, triple point of water. I sort of remember hearing something about that in a high school physics class or someplace. So what is triple point of water?
Okay, the triple point of water is the point at which we have solid, liquid, and vapor phases in thermal equilibrium. The International Temperature Scale of 1990 is founded on triple point of water as the base for the interpolation instrument, which is the standards grade platinum resistance thermometer, or SPRT.
Okay, and we actually have an SPRT here today. We're going to use that at some point. But as I remember from physics, wasn't that the definition of 0 degrees C?
Well, it's actually 0.01 because there's a pressure difference between one standard atmosphere, the ice point, and there are also differences associated with the dissolved gases in the water that make up the total difference of 0.01 C, the difference between 0 and the triple point of water.
Okay, so you actually make instruments that are able to create that triple point of water, right?
That's correct.
Why don't you tell us a little about that? Why don't you show us what that is and how that works?
Okay.
Let's see, I need to make this big, and then so, there we go.
As I mentioned before, the ITS 90 establishes the triple point of water as the base point for all interpolation up and down the scale. What's illustrated here are the various sub-ranges using different fixed points within the sub-range with the triple point of water as the base for all of those sub-ranges. The fixed points themselves are constructed using an envelope so that the outside pressure at local atmospheric pressure is not a factor in the realization of the fixed point. In essence, we utilize a pure material inside an envelope with the intent being to realize a plateau where if we freeze the material and then add energy to it, we bring the temperature up to the melting point of that material, or where the solid material begins to melt. Then any additional heat input does not produce any sensible temperature increase until we get to the point where we've completely melted all of the material inside the cell. Then there's a temperature increase that's sensed by the SPRT.
Okay, so what that means is you basically have a temperature that you can hold. I mean, you realize a plateau. It stays at that same temperature over time for a certain amount of time.
Correct.
But you can't hold it forever.
You can't hold it forever.
Okay.
But there is a significant period of time varying from a few hours to many tens of hours.
Really? Okay.
Yes.
All right, so tell me about triple point.
The triple point itself is illustrated by this diagram where we've got solid, liquid, and vapor phases of high purity water. It produces a pressure temperature diagram, one temperature at the triple point where all three phases coexist, and one pressure. The point that we're interested in, because I'm interested in primary thermometry, is the temperature point. By definition, it's 0.01 degrees C. That temperature then is measured using an SPRT, or standards grade platinum resistance thermometer, utilizing a 4-wire connection to a high purity platinum element suspended in such a way that is relatively strain free.
And so what's the typical value of an SPRT? Resistance value? Resistance
value for most SPRTs that are used in reasonable temperature ranges is 25.5 ohms.
Okay.
There are at high temperature SPRTs that are down in the 2.5 and even quarter ohm.
Wow. So to measure that, you got to be pretty careful.
You got to be.
What kind of concerns do you have in trying to make a measurement on a 25 ohm resistor?
Primarily looking to maintain a 4-wire connection in performing the resistance measurements, and the other consideration, primary consideration, is self-heating of the resistive element, because to measure resistance we have to pass a current through the element. By the act of passing a current through that element, we dissipate some heat in the resistive element. Okay, so and that heat's got to go somewhere.
So basically, where there's current and where there's resistance, there's power, there's heat.
Correct.
It's like your toaster, right? push the thing down and it gets red hot. You don't want that to happen here.
Yeah, we're not putting quite that much current through it, but the effect is the same, yes.
Okay.
So this illustration is of a thermometer down inside a triple point of water cell. The power being dissipated by the resistive element is illustrated by the purple arrows. That power produces a temperature gradient from the theoretical definition of the triple point of water, the phase equilibrium between the liquid and solid phases in this case, and the sensing element itself. That temperature gradient can range from a few millikelvin up to several tens of millikelvin or higher, depending on what the excitation current is. So that's the reason you need to pay attention to setting up the measuring instrument carefully to pay attention to the self-heating.
Okay. So I think I got the theory down a little bit. Triple point of water is I've got ice, I've got water, and I've got what you call vapor. We might call air or something like that. Okay.
Yeah, it's not air.
Not air. Okay, vapor. And the three of these coexist at the same time.
Correct.
Right? And that is defined as 0.01 degrees centigrade.
Correct.
Okay. So you still just sort of talked about how you might create that and how you measure it. Let's do it for real.
Okay.
So we got with us today a third visitor who is stands. This is what, the K51?
Correct.
Tell me what that does.
K51 is a thermoelectrically cooled core that in this case has cooled the cell down to approximately 8 degrees Celsius below zero.
So the water is less than degrees than
The
zero?
water is less than freezing. In fact, you can see a little ice on the outside of this envelope, kind of attesting to the fact that, yep, it's below zero. It's forming a little bit of frost there and dew condensation on the outside. So the liquid water in this cell is cooled to approximately 8 degrees below zero. If we agitate that cell by shaking the top of it, there will form a nucleation site, and one crystal will start, and then those crystals will propagate down the length of the cell.
Okay.
So I'll
can
hold
we
the
see
bottom
that?
of the cell, and we'll agitate it, and it will form ice crystals
Cool.
down the length of the cell. Now
Look at
the
that.
water inside this cell now has warmed up from approximately 8 degrees below zero to 0.01. The ice has formed, which will now act as a buffer, maintaining that 0.01 C for a long period of time.
Okay, so
in this case, approximately 8 hours inside the maintenance
Okay,
system.
so we've got ice, we got water,
Yep,
and we got air.
we got not air.
We got vapor. Okay,
Yes.
good. All right, so we put it back in.
So that cell will go back in the maintenance system. We'll change the set point from -8 up to a value that will maintain it for approximately 8 hours. And then we can use that instrument then to make actual measurements.
Okay, well, let's try it. So while you're setting the set point, I'm going to grab this SPRT, and I got to be careful. This thing, by the way, where you can buy cheap little resistive devices to make temperature measurements for a few bucks. This thing is what, Stan? A couple thousand?
Yeah, a couple $3,000.
Whoops.
Yeah,
Okay.
you don't want to do that.
Okay.
The thing that's a little bit tricky too is that the instrument may be a couple of $3,000, but you can spend up to $5,000 just having it calibrated.
Okay, and this one, by the way, has been through the ringer a little bit. You can tell if we look at it, it's gotten hot and other things. We also haven't calibrated this in quite a while, so it'll be interesting to see how close to real we are. I don't doubt that you are truly at 0.01.
And the uncertainty on this instrument is approximately half millikelvin. The uncertainty on that instrument, the combination of the two, is somewhere between 5 and 7 millikelvin. So you've got a good ratio between the standard and the unit being tested.
Okay.
Calibrated.
So I'm actually using a 34420A. This is Agilent's nanovolt micro-ohm meter, and we're going to do we're doing resistance measurements. So we're actually on the 100 ohm range, and we put it in the low power mode because of what you talked about. We don't want to heat up the element. We're also doing 4-wire ohm, obviously, and we have some other things in here like offset compensated, and we're doing some other magic trying to take the best measurement possible. So can I do the honors?
Yeah, absolutely.
All right, I'll try not to break anything. I slide this down into here. Eventually it'll stop. Oh, okay, I found the bottom. Okay, so we've waited a few minutes. Things have reached an equilibrium. They've equilibrated, as the term is used. And as I look at it, I don't seem to be at 0.01 degrees C. So something's going on. I've got about a 30 millidegree Celsius offset. So what I'm going to do is go in and actually measure using a low power 4-wire ohms technique and see what the resistance really is at this point with my SPRT. So to do that, I'm going to go to 4-wire ohms, and it measures 25.2734. Okay, so I'm going to go in and see what I've got set up actually under the RTD. What did I set it up as? And it looks like instead of a 25.2704. Okay, so I want to come across, take that digit, bump it by 3. That was the measured value. If I enter that, okay, now I'm going to go back to temperature. Up, and look at that. It's 0.01 degrees C with a, 1 or 2 bouncing around on the least significant digit. So it seems to work. Okay, so we've gone through quite a few things today. We've talked about what the heck triple point of water is, right? Stan's explained that to us. He's explained how to realize a triple point using the techniques that he's got built into his product, right?
Correct.
And finally, we've shown how to use that to calibrate a system consisting of an SPRT and a measurement device to be able to accurately measure.
Correct. And the uncertainty of the triple point of water in this situation is approximately a half millikelvin, and the ratio between that uncertainty and the uncertainty of the instrument and SPRT combination at about 10-to-1 ratio.
Okay. So hopefully this has been interesting to you and entertaining, and we'd look forward to seeing you next time.